early because you're so excited to see these talks today. I didn't have to clap out there or anything. So welcome to our astrobiology seminar today. It's going to be a couple of rotation talks from local graduate students. First up is going to be Megan Gialluca, who is going to tell us all about her experiences working with spacecraft and what the implications are for HWO. So we'll hear from Megan for about 25 minutes, and then we'll switch and we'll hear from Autumn in the second half of the hour. All right, please take it away.
Thank you. Okay. Hi, everyone. Thanks for coming. I think I know pretty much everybody in this room, but for posterity, my name is Megan Gialluca. I completed my research rotation this summer working on stray light effects of defective primary mirror area for the Habitable Worlds Observatory. In particular, we were interested in damage from micrometeorite impacts, which, as some of you may or may not know, has been an issue that we've seen on the James Webb Space Telescope. And before I get started, I just want to say, thank you so much to Dr. Chris Stark, Dr. John Ehrenberg, and Dr. Aki Roberge, who were my research rotation advisors over the summer. Okay, so this is pretty much what I've said already, but I spent last summer collaborating with Habitable Worlds Observatory TAG Technological Assessment Group members to explore stray light constraints. Overall, our goal was to evaluate the effect of telescope and barrel designs on stray light and micrometeorite damage as a function of mission lifetime. And I'll just mention that this picture is relevant because I got to see the redwoods when I was down in California. Okay, so I want to remind everybody of the language in the Astro 2020 Decadal Survey. The survey stated and charged HWO with observing approximately 100 nearby stars and successfully detecting potentially habitable planets, aka Earth-sized planets and habitable zones of at least a quarter of those systems. And then furthermore, it wants to, for the most exciting 25 planets, use spectroscopy to attempt to characterize their atmospheres. And so I like to think of it very simply as being charged with two phases. Don't necessarily have to be one after the other. They might be occurring at the same time, but you need to observe 100 sun-like stars and attempt to detect planets. And importantly, you have to confirm that the planets you detect are in the habitable zone. And then phase two, you have to take high resolution spectra of about 25 of those habitable zone planets. And so overall, we have this mission lifetime, and we know that HWO has to accomplish these goals across this lifetime. And now the issue is that to do either one of these things for Earth-sized planets is incredibly difficult, and you need very high sensitivity to get to very low contrast levels. And the issue is that you can do all you want to your telescope, but the minute you send it up into orbit, it's going to start degrading over time. And the primary reason for that we considered was micrometeorite damage. So I want you to imagine that we have a telescope with some primary mirror, some secondary mirror, and you're trying to look at a specific star, the orange one in this case, and its system. In a perfect world, you have an ideal mirror, and all of the light from your field of view gets perfectly reflected into the secondary mirror, into your detector, and all of the light from the background stars does not make it into that image plane. Then you have a micrometeorite hit, and all of a sudden, you have some damage on the mirror that's no longer a perfect reflector, and that damage can now scatter light from outside of your field of view into your observation. And so this is something that we see, of course, happening on the JWST. This is showing wavefront error. It's not exactly the same as stray light, but it demonstrates the idea. It's a before and after shot of a rather large micrometeorite hit to one of the segments, which you can see right here. And so one of the things you can do to try and mitigate not only the stray light you're getting, but also the number of micrometeorite hits that you have is to just slap a barrel onto your telescope. And this is one of the primary reasons why, if you look at all of the concept art for the upcoming HWO mission, you'll see all of them currently have barrels on them. So once again, that blocks out stray light. It also blocks out micrometeorites. And so in this work, our goal is to provide reliable order of magnitude calculations for stray light as a function of defective mirror area for different barrel designs. And this allows us to better assess the threat of stray light very early in the mission design process when we can do something about it. Okay, so now it's going to get a little ugly. So I want to consider scenario one, which is what I call the host star only scenario. So we have these field of views, right? If you look up at the night sky, you see a ton of stars, and all of those can be potential light contributors. But in the very most simple case, you have the host star, which we're trying to block out, of course, with the coronagraph, but all bets are off once you have damaged mirror area. And so the host star for damaged mirror area can be a contributor of stray light. And since it's directly in your pointing direction, it is, as we will find out, the largest contributor of stray light in many cases. And so doing this scenario makes the math nice and easy. We have the host star, and then it hits the primary mirror, which we're treating as a point source for now. That primary mirror, the damaged area at least, will scatter the light back up into the secondary mirror. And we're really interested in the amount of stray light that falls within the solid angle of the planet's point spread function. So that sounds very complicated, and I still don't really understand PSFs that well. But what you need to know is that this is basically saying we're looking at the amount of stray light that's going to fall onto where the planet is going to fall onto in our image plane. Okay, so I'm going to show you a little bit of math, and I promise this will be the only equation, but it's important for understanding the results. So let's consider that light received from the planet of interest must be greater than the stray light from the host star that is scattered by the defective mirror area. This is a somewhat arbitrary decision for a stray light requirement, and I'll talk about this at the end of the talk. This doesn't necessarily need to be a strict requirement, but it's an easy one to conceptually grasp. You know, in a perfect world, I think, sure, we would love for our stray light to be less than the light of our planet. So let's start there. You get something that looks like this. It's very ugly. All it is, on the left, we're saying the flux of the planet times the entire area of the primary mirror. So the light that's reflected has to be greater than the flux of the host star times the damaged area times this ugly looking integral. All this integral is what's called the BRDF, or the bidirectional reflectance distribution function. This defines the scattering properties of the damaged area. So if I didn't have this integral here, we'd basically be saying that the damaged area is a perfect reflector, which it's not. The BRDF to first order is telling you what fraction of light that's hitting your mirror area is being reflected back into the direction that you're interested in. So into that planet's point spread function. And so if you do some rearranging here, you can get to a requirement of the maximum allowed defective area before the stray light requirement you have decided on is violated. And so that's really important because, once again, I can just replace the left side of the inequality with whatever stray light requirement I want. But we're going to start here. Okay, let's talk about reflectance. Surfaces can have two primary types of reflectance. Number one is diffusive reflectance. It's also called Lambertian reflectance. This gets very complicated, and this is actually like a funny story that I won't go into too much, which is a classic. Here's where engineers and astronomers speak a different language. Because when we say Lambertian reflectance as astronomers, we're quite frequently referring to equal light as reflected in all directions, such as me scattering. Whereas when an engineer says Lambertian reflectance, they actually mean it's a cosine scatterer. So at the end of the day, more light is reflected in the surface's normal direction. But that's all I'll say on that. Don't worry if that made no sense at all. Okay. So important thing is diffusive reflectance doesn't care about reflectance direction that much. So it's really, you can first order think of it as light gets scattered equally in all directions. And then we have the other type of reflectance, which is perfect specular reflectance. And this is what I'm representing by a Dirac delta function. And so specular reflectance is saying that the light that's coming in at an angle of theta will then be perfectly reflected back in an angle of theta. And all of the light that comes in is all perfectly reflected. That's specular. And so you might be thinking, like, why can the BRDF go to infinity if it's a fractional amount of light? It's because there's a per steradian dependence. So the BRDF is not a unitless quantity, and I won't go too much into this, but the idea is that it goes to infinity at the angle of reflection because it's saying that for an infinitesimally small solid angle, all of the light is reflected into that angle. In reality, surfaces, especially damaged area, are going to be somewhere in the middle with these two. So this is a classic Phong reflectance model, which combines components of both Lambertian and perfect specular reflection. And it's defined by some reflectance of diffuse reflectance and a reflectance of specular reflectance. And then this end term, which isn't that important. The end term just tells you how sharp the peak is. And so you can see that for various types of reflectance surface properties, this is going to get sharper or broader. And the idea is that we want to explore all of these possible scenarios. And so the varying degree of, let's say, specularness tends to govern how much stray light a particular mirror defect can contribute. This is especially true in the host star only scenario. The reason for that is the host star is in your pointing direction. And so any light that gets specularly reflected is going to be really, really bad. And what I'm showing you with this Phong reflectance model is essentially from the blue to the red is more specular. And what you can see is that as that peak becomes more sharp, so for different values of n, which are your kind of like a power law exponent is a good way to think of it, you're really turning down the amount of damage you can sustain by orders of magnitude. And what I think is interesting that's shown here is the actual reflectivity of your surface has less of an effect. But this is, again, not too important. I think it just continues to demonstrate this idea. I do want to point out that for contributors not in the specular direction, diffusive scattering is going to be a larger problem. But moving on, we have three categories of defective mirror. Of course, we're mostly focused on the one in the middle, but let's just talk about these other two for a minute. So mirror roughness, this is given really an industry standard as the Harvey-Shack model, or what's called the ABG model. And what I mean by mirror roughness is that no surface is perfect. And so we coat these surfaces the best we can, but if you get down to microscopic scales, they're going to have some sort of roughness on them. And that's what's being shown by this figure here. And so ideally, right, you have the specularly refracted beam, but then you're going to have other beams that are reflected just by the roughness of your surface. And so this is what the Harvey-Shack BRDF looks like for different angles of incidence onto the surface. In every case that you're going to see, if you have something coming down at an angle of 0 degrees and going back up at an angle of 0 degrees, that's how you get the most amount of reflection. It gets a little bit weirder too when you get to like very large angles. So these are called grazing angles where it comes right off the surface. But what I really want to point out for Harvey-Shack is that the y-axis here is in linear scaling, and it only goes up to like 1, and that's not very large at all, is what you're going to see. So because of that, for the host star only case, if your entire stray light budget, let's say, was allocated to mirror roughness, you'd be able to tolerate a roughness of up to 190 angstroms. And so I mean by 190 angstroms is describing the size of those, let's say, jagged edges there. And that is actually very, very big. For reference, typical numbers are like tens of angstroms or less. And so we're not really worried about mirror roughness. This is not going to be your, let's say, constraining consideration. Then we have contamination or dust. And the industry standard here is Mie scattering of particles on a reflective surface. Make that distinction because, again, astronomers will think about Mie scattering of dust particles in space, but we're going to put those dust particles onto a mirror and all of a sudden things get a million times more complicated. So this is, as it turns out, very difficult to do analytically, so I didn't. And this is a result that we're still working on because it's very, very complicated. But the idea is that we're really trying to generate these curves with very robust software for scattering light. And then we're going to try to interpolate between curves to put this into the model, which I'll talk about later on. So I'm not going to spend too much time here. What I will point out is if you look at the y-axis, all of a sudden it's jumped up to log scaling and it goes up to like 10 to the 6, which is very large. So Mie scattering can be quite a large contributor of stray light. That's why they talk about cleaning the mirrors so much before they launch them into space, because you really need to clean them very, very well. And one thing that I definitely heard kicked around a lot is, you know, do we need to clean the mirror throughout the mission, for example? So all things to consider. And then finally, we come to micrometeorite damage, which in this case, we're going to use what's called the Peterson model for digs. And I won't go too much into this, but on a mirror, of course, you can have digs, you can have scratches. So I mean like little imperfection areas, and a dig on a mirror is very similar, akin to a micrometeorite impact crater. And so that's why we go with this model, which has been done by a few groups in the past, including for the LISA mission. And this model, you need to understand how a particular impactor's mass or impact energy relates to the size of the crater or the dig that it's going to produce. And as it turns out, this is very, very unknown. And so these are for different types of materials. All of these are different models. Again, notice the log scaling on both axes. And so these models are varying widely in how large of damage they're predicting a particular impactor will give you. So that's something to keep in mind. With that being said, we took the most optimistic and pessimistic models out of there to focus on. So we have Watts and what I'm going to call the MR model. Similarly to Harvey-Shack, this is showing you for different angles of incidence, the BRDF value for different scattering directions. And they look identical, which makes sense because we're using the same BRDF model, just a different relationship between the size of the impact crater. And that's reflected in the y-axis. So you can see the MR model is predicting much more reflectance into near specular directions. And so that means that MR is a little bit more pessimistic for the host star only case. Okay, so here is that allowed damage fraction, that sort of equation we worked through a few slides ago for both of these models. And you can see that the maximum allowed damage goes from incredibly large, and you're probably going to be fine, all the way down to don't even launch the mission, because why bother? So that's the issue that we're facing. And I don't have this result to show today. It's still, we're kind of working at the kinks, but in general, I've been trying to convert this to an idea of at what impactor mass is it one impact and your requirement is violated. And it turns out it's about maybe, let's say, 2 orders of magnitude optimistically greater than the impact that fell onto JWST back in May. So it's not great, is what I'll say. But also keep in mind that our stray light requirement is not very strict at this point. Okay, unfortunately for us, there are many more sources of light than just the host star, which is what we've talked about. And so this host star only case is by definition an optimistic case. Additionally, the mirror is not a point source. And so when you start talking about spatially resolved sky, you also have to start talking about a spatially resolved mirror. And so what I did this summer was I built a model that models a spatially resolved primary mirror plus barrel geometry, and it simulates essentially observations onto the sky plane in order to determine what is the contribution of stray light from every point on your sky. And so we're going to go back to this math just for a minute, just for a second. And we have this BRDF. I'm going to put the full idea in there for a minute. Now let's think that we have a sky area divided into n sub s points, which is observed by a mirror that has n sub dA number of aerial points. All of a sudden, this equation becomes something that looks like this, and it's awful looking. But we can break it down. We're not even going to talk about the math here. We're just going to say that it's the stray light flux requirement divided by the sum of all flux contributions from every sky point onto every mirror point. So I think importantly for modeling, you have to do n sub s times n sub dA number of calculations to get an idea of how much stray light you have coming in. And for now, we're going to assume that all of the damage is equally spread out across the primary mirror. This model, I'm not going to go too much more into it past this point, but the model that I'm working with, it would be very easy to say I want to assign all of the damage to one point or a few different points. So if that's something you're interested in the future, we can definitely do that. So the first thing I had to do was figure out how I was going to simulate these observations. So I created these compiled maps of Gaia data using supercomputer. It was very fun. This actually was fun. And what I'm showing you is 3 different pass bands of flux. So G band, V band, and IC band. We're going to move forward with V band, which is best for HWO at this point. And then up in the top right-hand corner, I'm showing you the total number of sources in each bin. I want to stress that this is every single source in Gaia's VR3 catalog, which is a lot of sources. And you can see the large and small Magellan clouds, which is pretty cool. Okay, so here's what the model looks like, or at least a representative visual. So the first thing that happens is we generate the telescope model for whatever barrel geometry you want. And importantly, we can rotate that with respect to your sky plane. This is important because you want to put the longer side to wherever the sun is going to be. Then we determine how those sky points are going to be able to access mirror points. So what I mean by this is like a sky point on the rim, or sorry, a mirror point on the rim of the telescope will not see the same area of sky that a mirror point in the middle of the primary mirror will. It's going to be a little bit shifted. And so I'm representing this for you with these plots, which are showing you the fraction of primary mirror area points that each sky point can actually access, that has a clear optical path to. And so the model itself will actually go through and calculate the stray light contribution for each one of the points on your primary mirror for every single sky point that it can see. And then finally, what I'm showing you is what that sky background is going to sort of look like to your telescope when you model an observation. And this is my representative visual. And I think importantly, we're handling a lot of edge cases in this model, which are shown in the middle. So longitude wrapping, when you go below a longitude of 0, galactic longitude, comes back around to 360. And then the very, very difficult one was the meridian flip, because as you start to look towards the galactic poles, you're actually seeing all galactic longitudes. Okay, so one of the first results that came out of this was to just look at what I'm calling the entire pointing box. And so if we look back at these maps for just 1 second, we can see that if you're looking for a particular target, it's going to fall in one of these grid boxes. And in each of those grid boxes, you could have a lot of sources. And the issue is that as you move towards the specular direction, each one of those sources is going to have a larger impact on your stray light. And so in general, it's a good approximation to just sum up the flux contributions in a particular grid point and then calculate that grid point's distance from your pointing direction. But once you get into the box that actually contains your pointing direction, that approximation starts to break down. And so for a given target, we actually calculate the stray light contribution of each individual resolved source. And so what I'm showing you here on the left is the allowed damage fraction from that equation that I showed you as a function of host star luminosity and galactic latitude. And then on the right, we're seeing how that damage fraction changes when I consider that target's entire pointing box. So all of the sources that are relatively close to it. And the important results here is that even without the pointing box, stars with very high luminosities are going to tolerate much less damage for the same requirement. And that's because they're producing a lot more light. Once you consider the pointing box, though, you also are going to have a cut for stars that are very close to the galactic plane, which makes sense because there's a lot more sources there. And so what you might take away from this is if we're only considering this analysis, let's say for now, you might want to give observation priority to targets that are high in luminosity or close to the galactic plane, because you want to get those targets out of the way before you lose the sensitivity to observe them. Okay, so the analyses that are currently in progress. Well, number one, we want to actually consider those barrel geometries because the pointing box is going to be visible for all barrel geometries, unfortunately or fortunately. I mean, that's kind of the point of the telescope. So we want to put barrels on there and then do full stray light calculations, which I'm actually running right now as we speak. We want to look at optimal barrel rotation. So if I spin that barrel around in the best way, can I actually reduce the stray light by a considerable amount? And the reason for doing this is because if that can reduce stray light quite a bit, then it's something you might want to build into, say, an architecture. And then finally, we want to connect micrometeorite damage and stray light to habitable worlds observatory yield calculations with AYO. Let me explain this a little bit more. What is yield? Yield is basically across the lifetime of your mission, how many Earth-sized planets do I think I'll be able to detect and characterize for some of those? But let's just focus on the detection part for now. The stray light requirement I've shown you does not mean that once we violate that, that's it, mission's over and you can't do it anymore. Just means that the required exposure times you're going to need for each target are just going to start going up and up and up and up. So you have to spend more and more time integrating over one target to try and detect a planet. And so instead of saying we're going to have a particular stray light requirement, a more useful quantity in a lot of cases is saying, how is the stray light going to affect this science yield of my mission? So how many less Earth-sized planets am I going to be able to detect if we just have this particular barrel geometry? And so to drive this point home, this is if I change the stray light requirement here to what's called exozodi, which is a sort of representative amount of light for dust in your exoplanetary system. You might have remembered Miles Curry, who did a lot of work on exozodiacal dust. And so as the exozodi requirement increases, so does the allowed amount of defective area. And all of the targets you're seeing here are all the targets in the XEP target list from Amajek and Staplefeld. And then on the right here, I've just pulled out an exozodi of 3 requirement, which is pretty typical. And if we use that instead of the previous requirement we're talking about, the allowed amount of damage for about 90% of sources actually goes up by, in some cases, an order or 2 orders of magnitude. So the straight light requirement is what I'm trying to drive home here, is not necessarily the end of the story. And so, yeah, that's what I just said. Okay, so AYO is an optimized yield calculator from Chris Stark. And so this is a calculator that takes all of these parameters for your mission and says, I'm going to simulate trying to visit these systems over and over again and see if I can detect planets. And so this is a good representation of what AYO does, which is showing you that here's some target system. And all of these are the different orbits of a habitable zone planet you could have there. And on visit 1, all of the red dots are the places that you've ruled out or detected a planet if it's there. On the next revisit, you've ruled out even more places where a habitable zone planet can be. And then all the way down to the 4th visit, you can see that almost all of the dots are colored in now. And that means that we have explored that system to a very high degree of completeness, which means if there was a habitable zone planet there, we would be very likely to have detected it, or we did detect it. And so what we're doing now is we're going to add in numbers of stray light that might be representative of 1, 5, or 10 years into the mission for different barrel geometries. And we're going to see how the yield predicted by AYO decreases over time. So here it was results from AYO. Actually, it's not this. These aren't from 2014. These are from like 2016, which is telling you how many exo-Earth candidates you can get if you allow 1 or less than 20 visits per system. And then the total number of stars you're able to observe that are different. And I don't have these results today, so I just kind of showed you what we expect, which is that these curves are going to go down. You're going to be able to observe less targets. The question is how much? Okay, so this is my research rotation slide. I got to do a lot of fun things besides science. I was in LA and then I was in the DC area, and David was there. There's David. David, our very own David, was down there in LA, so I got to see David for a minute. Yeah, and in my free time, I learned how to do handstands on other people's hands. Okay, so here are my conclusions. Stray light due to mirror damage can obstruct the goals of HWO, and mitigation and observation strategies with precursor surveys or even technology should be considered very, very early. One of the issues with large space-based missions and why they get delayed, let's say sometimes, is that people rush into building and investing money in things without doing sufficient amounts of work beforehand to understand what we're really doing. So that's why we want to do this super early. The relationship between micrometeoroid mass, impact velocity, and damage varies widely in the literature, and it should be further studied for materials that we want to use for HWO, because that's going to impact how much stray light we're going to take on. And then finally, it might be necessary to develop strategies for mitigating damage after a large impacting event. Even if you're only likely to have one really bad impact in the entire mission lifetime, if you launch that telescope and the impact happens in year 1, what are you going to do, right? So with that, I will end my talk here. Thank you.
Thank you so much, Megan. We have time for a few questions.
Josh?
Yeah, thanks, Megan. That was fascinating. I'm just curious, do you know if, like, the possibility of swapping out damaged mirror segments is part of the serviceability discussion, or is that too difficult? You have to just patch them with something that paid to.
It's so funny that you mentioned this because I don't think I think John would be mad at me if I talked about this too much. We had a lot of debates on like how do you do mitigation after, and I'll tell you about the idea that I came up with, and it horrified a room full of engineers. They were like, "We're never gonna do that," and I was like, "You guys need more creativity." I wanted to do shark tooth mirrors, which is where this is my description. You pop the mirror segment out, and then the next one comes in from the bottom.